really important in mathematics and calculus next year, because we want to take derivatives of continuous functions, or we need to find out where it's not continuous. So here's what I'm going to do today. I'm actually going to tell you what a continuous function is, kind of give you where it's not continuous. Then there's a 3-part definition. It's going to sound very mathy. You're going to be like, I have no idea what you're doing. I'm just copying notes. Just do that. Sometimes it helps. Then we're going to do examples. When I do the 3 examples, I promise you it'll kind of start clarifying in your head. Oh, okay. And if you're still struggling, I got to listen. All right. So what does it mean to be a continuous function? Here's like the little kid version of it. Okay. This is like what I call the little kid definition. It is a function that has no holes, no breaks, or gaps. You want it to be very smooth. You want it to keep looking pretty. You want to put your pencil on it and trace it and not have to lift up your pencil. You can trace the graph without lifting a pencil. Okay, that's just like the little kid version of what it means to be continuous. I'm going to give you the actual like mathy definition in a minute. But before we get there, let me show you types of discontinuity. Okay, so I just said what it means to be continuous. But let me show you what it means to be discontinuous. Types of discontinuity. There are 3. Okay, number 1 is what's called infinite discontinuity. I'm going to draw a little picture over here and even give you the equation so you know what's going on. Your basic infinite discontinuity would be something like this volcano shape right here. This is f of x equals 1 over x squared. Okay. Why do you think this would be infinite discontinuity? Or why would they call it that? Go ahead.
Because it keeps approaching one value, but never reaches it for eternity.
Yeah. So again, if you kind of go back to my little definition up here, you can trace the graph without lifting a pencil. If you start tracing this graph right here, doesn't your pencil seem to like go off into infinity to me? You would never be able to get to the other side. Okay. So that would be what we call infinite discontinuity. It's where there's asymptotes. If you have asymptotes, you have an infinite discontinuity at that point. All right. So that's your first picture. Second type would be a jump discontinuity. Anybody know what jump discontinuity look like? You've graphed them before, but like piecewise functions are usually jump, usually. Not always. But here's a piecewise function. This is x when x is greater than or equal to 0. This is x squared plus 1 when x is less than 0. Okay, so that's a jump discontinuity. Again, why is it jump? Because if I try to, again, put my pencil on it, I'd have to jump down to then keep going. So I have a discontinuity at that point right there. Now, these two together, next year, I don't think this year, but I'm going to let you know about it right now. These are actually what we call non-removable discontinuities. Fancy name, these two right here. They're called non-removable. You can't remove them. But pretty much if you have an asymptote or a jump discontinuity, it's non-removable. Can't remove it. All right, and then your third type of discontinuity is what's called point discontinuity. This one's very deceiving. And I will actually give you a picture right now. If you were to put this in your calculator, f of x equals x squared minus 1 over x plus 1, it actually just looks like that. But you would never know this, but there is a hole in the graph. There is a point where there's a hole. And the only way you could tell would be looking at the table in your calculator. there would be a hole right there. That in mathematics is called removable discontinuity. Holes are called removable, okay? So these are your three types: infinite, jump, and point. Those are the types of discontinuity. Just so you know, and put a little star around this. If you are a linear function and you're a quadratic function, linear and quadratics, they're always continuous at every point. What do you mean it has to be both? No, if you're a linear function or you're a quadratic function, you are continuous at every point. Every point you're continuous. All right, so basic definition of to be continuous function, the types of discontinuity, but now we're going to do the proving it's a continuous function or not at a certain point. And this is where the definition gets really like mathy, but just don't worry, write it down when we're done. So the continuity test is for a function f of x is continuous at the point x equals c if it satisfies the following. Okay, so number one, you have to have f of x being defined at c. Meaning you have to be able to put in the value that they give you at that point, and it has to exist. Well, when would it not exist? Well, things don't exist when you divide by 0. Things don't exist there, right? Can't divide by 0. Things don't exist when you take a square root of a negative. Those don't exist. Okay, so those are really the only times that they don't exist for right now. Okay, so step number one, it says f of x is defined at c. F of c exists. Here's the little like shortcut version. Plug it in, plug it in. That's what you're going to do. The first thing you're going to do to test the continuity. You just plug in the number. If you get out a number, good to go. If you get out a number divided by 0, you can stop right there. You failed test 1. It's done. And that's going to happen on tonight's homework. You're going to love those problems. You're going to be like, I'm done. It failed test 1. Woohoo. Okay. So that is a great thing. All right. Number 2. Now this is where, again, it's going to sound really mathy. Just write it down. F of x approaches the same value from either side of c. Okay, in calculus and in pre-calc, this is what we call a limit. And this is what I'm doing all next week with my calculus students. We're doing limits. It's very important to find out a limit. When you approach the same value from either side of c, you don't have to necessarily be that point. You just have to be near that point. Like just for example, we have limits in our everyday life, like a speed limit, right? If you were going 49 and a 50, you think you would get pulled over? 51? No, you're approaching that limit. You're okay within that limit. You don't necessarily have to be at 50. You're still okay. Okay. So again, the mathy way of writing it, you would say the limit as x approaches c, it actually, you write lim, of the function, does it exist? That's what we're looking for in this number 2. Well, how are we going to prove that it exists, Mrs. Setta? Well, you're going to do the following. You're going to use a calculator and make a table. That will be your second step that you will do. Again, if what I just said is too mathy for you right now and you don't understand it, it's okay. I promise you when we do an example, it'll kind of clear itself up in a minute. All right. Then the third thing, you've passed test 1, you've passed test 2. You have to then check test 3, is that the value that f of x approaches, bless you, from either side of C is the same as f of C. Again, mathematics-wise, this is what I'm saying. The limit as x approach C of f of x, meaning what I just found out in number 2, was the same as what I got in number 1, f of C. This, what I got out here, is the same as what I got out in number 1. So that's my little trick here, that your number 1 is equal to your number 2. Okay? All right. Now, whoo, we got this. I'm going to do 3 examples right now. If I lose you on the examples, you got to tell me where I lost you. Okay? And then we're going to do some classwork, and then it's going to all determine whether each function is continuous at a given point, and then justify. Here's our first example. F of x equals 2x squared minus 3x minus 1. Now, if you're paying attention, if you wrote this down, what is this? What kind of function is this? A quadratic. What did I just say here? It's continuous at every point. It doesn't matter what point I gave you. It is continuous at every point. So guess what your answer is going to be when we're done proving it? Guess what your answer should be? Yes or no? Yes. Yes. Okay, you all with me? We all agree to that. It's got to be yes, Mrs. Setta. God bless you. All right. So we have to justify. This is the fun part of tonight, which is like doing proofs back in geometry, but it's not that bad, okay?
Can that say just for justify, just quadratics are always continuous?
No, we have to go through each 3-step. Fun. Okay, so step number 1 for test 1 of the continuity test. All right, so looking at my notes, this is why I give you things. F of x is defined at C, f of C exists. Mrs. Setta said, plug it in. So that's going to be what you do first. Plug it in, plug it in. Take your 2, x equals 2, and you're going to plug it in. 2 times 2 squared minus 3 times 2 minus 1. And tell me what you get out. 8 minus 6 minus 1 equals 1. I do get out a real number. It exists. So I have passed test 1. The only time, again, this will not be existing is if you divide by 0 or get like a square root of a negative, then you could just stop right there. But we got to keep going. All right, so we plugged it in. You can write this down if you want to, but that's what we did. Number 2, now here's the fun part. We are going to make a table, and I'm going to show you why. So I want you to get out your calculator. I want you to type this into y equals. I'm actually going to prove this test by looking at a table of values. Here's why. Test number 2 says that the function approaches the same value from either side of C. From either side. It has to, in math terms, it's called the limit, again, that you approach the same value from either side of C. So using a table is actually going to help us, but we actually have to change the table. We actually have to make it get really, really close to our C value. Again, what is our C value? Is it 1 or 2? It's 2. This is our C. This is the point we're concerned about. Okay? So you are going to go to second table set. Second window, I guess is what you can say. Do you have this right here? You are going to set your table to start at your C value, which is 2. Okay, so I'm going to put my 2 here. The triangle table means the change in the table, meaning what do you want it to go up by? You want it to go up by 1s? Yours probably says 1. I want you to go up so close. I want you to be very tiny and very precise. So I want you to go up by 0.01 almost every time. When you get to calculus, you would actually go up by 0.001 sometimes. We actually go even tinier, okay? So that's what I always want you to start off with. Then you're going to go to second graph. Second graph, and you're going to go up 2 spots. And you should have a table like mine. Look right now and make sure that your table looks like my table. Does your table look like my table? Okay. I want you to actually, for homework tonight, copy down the table. 2 spots above the C value and 2 spots below the C value. So here's what I mean. I want you to do 1.98, 1.99. 2 is your C value. 2.01 and 2.02. And then actually copy out the Y values. Let's see, 0.9008, 0.9502, 1, 1.10. Okay, so here's what we're doing. According to test number 2, does the function approach the same value from the either side? So here's either side of C. This right here, this side right here is x approaching 2. Here's the either side. Are we getting to the same number on either side? Is 0.9008, 0.9502, does that look like it's approaching 1? Yeah. What about 1.1008, 1.05? Does that look like it's approaching? And even if you went to even a smaller change in your table, like 0.001, it would even get even closer. So this is going to 1 and this is going to 1. If they're both headed to the same number, then you've passed test 2. As long as they're headed to the same number. So that's what I mean by make a table of values. All right, and then last one, test 3. So what am I asking you in test 3? Here's what I'm asking. That the value you got from what just happened in step 2, that limit, the f of x approaches either side of C, is the same value you got from step 1. Did I get that same value in step 1 as I got over here? I sure did. Okay. So you would say the limit, and you probably don't even have to write this. The limit as x approaches 2 of my f of x is equal to 1, which is actually equal to f of 2. These are both the same. Your number 1 equals your number 2. So yes, it is continuous at x equals 2. Oh, Mrs. Seta, I knew that from the beginning. I know, but you have to justify it now. It's a pain, but I promise you it helps you with calculus. Okay? All right. Let's do an even easier one. Function is x minus 5 over x squared minus 25. Is it continuous at x equals 5? What is the first thing that we have to do? Plug it in. Plug it in, plug it in. So f of 5 equals 5 minus 5 over 5 squared minus 25. Is 0 over 0 a real number? Does that exist?
No.
We say DNE. DNE means does not exist. Then your answer is not continuous at x equals 5. Done. Boom. Those are the problems we entire function into calculator. Okay, a lot of kids in the other class were not doing that. But for step 1, you could do it without the calculator. Plug it in. Where am I going to plug in x equals negative 3? Into the top piece or the bottom piece? Tell me why. Why the bottom? Because it's equal to. Okay, so the f of negative 3 is equal to 2 minus negative 3. What does that become?
5.
5. Okay, what that means is you exist. Okay. So I do have a value, so I passed test 1. I now need to go to test 2. All right, so for test 2, you have to plug the entire function into your calculator, not just the one piece, both pieces, or 3 pieces, however many pieces. Go to your calculator, everybody. Into y1, watch how I do this. You are going to type 3x minus 2. Now watch what I do. If it says if, or if it has a comma, you are going to put the division symbol. Put divide. Then you are going to put a parenthesis symbol. Parenthesis. Then you type x again. You see this like a greater than symbol right here? This is located in second math. So right now hit second math, go to your greater than, hit -3, not -3, and then close the parenthesis. That is y1. You are now going to put this second equation in y2. So you're going to type it just like it is again. You're going to type 2 minus x, divide, parenthesis, x, second math, God bless you, less than or equal to -3, close the parenthesis. Does yours look like mine, I hope? Okay. Now you can hit graph just so you can see what it looks like. It's kind of cool. So you can already see right there, there's this jump discontinuity going on. And where's that jump discontinuity happening at? Looks like it's happening at -3. Wonderful. But let's double check it with the table. So go to your table setup. Where do you want it to start at? Do you want it to start at 5 or -3? I'm trying to trick you here. Where do you want it to start at? -3. That is what we're concerned ourselves about. -3. We want it to go up by 0.1. Hit second graph, second table, and go up 2. Now you're going to see a lot of things like mine. You're going to see error, 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 error. That's okay. Don't worry about that. I'll explain that in a minute. Okay? So you're going to make your table -3.02, -3.01, -3, -2.99, -2.98. At -3.02, ignore where it says error, write down the value it actually has. It has a 5.02 value. This one has a 5.01, this one has a 5. For -2.99, ignore the error, write down this value, -10.97, -10.94. So again, on this side, my limit is approaching -3. My limit of x is approaching -3. But what am I approaching here and here? Are these the same value? What's this value approaching? What's this value approaching though? -11. Those are not the same. Again, when that happens, that means you do not exist as a limit. So guess what your final answer is? Not continuous at x equals -3. It's continuous elsewhere, but not at x equals -3. Okay? So I've just given you 3 examples.